Right, folks, hello again. Moving on with our ozone story self-study stuff, part 9. Having talked about the atmosphere generally in the last session, we now home in right onto the key feature of this topic, which is ozone. So we're going to look at ozone in the context of the atmosphere. We have met ozone before in the developing fuels topic when we were talking about pollution, and it's a secondary pollutant. Do you remember what a secondary pollutant is? And you should define that as a pollutant that forms after the polluting process. So for instance, if you're driving a car around, it doesn't come out of the exhaust pipe because the engine literally makes it, but rather reactions happen to the primary pollutants, the things that are directly produced in the atmosphere subsequently to make ozone. So therefore it's a secondary pollutant. Do you remember what the formula of ozone is? And you should say O3. So it's an unusual form of oxygen. So here's a little challenge for you. Can you figure out a dot cross diagram for the bonding in O2 and O3? So dot cross diagrams for O2 and O3. Pause the video, have a go. Start it again when you're ready. And so for O2, hopefully a bit more straightforward. Oxygen's group 16, 6 electrons in the outer shell. So it's going to get 2 more for each atom in order to get up to the stable 8. So it can do a double bond. So each atom gets 2 more. Don't forget to draw in the lone pairs. So with 6 of its own electrons, 2 in the bond, hence 4 electrons as 2 lone pairs. So that leaves a bit of confusion. How does O3 work? If oxygen satisfies its bonding like that with a double bond, how can you have 3 oxygens? You can obviously go, well, okay, let's have a single bond from this oxygen to another one, and then another single bond onto the next one. That's fine for the oxygen in the middle. 6 of its own electrons, it's seeing 2 more electrons for that atom. That gets it up to the stable 8. But the other 2, that way would only get up to 7. So that's not possible. I mean, it would be, it could form, and then it would be a radical, right? 2 unpaired electrons, making it super reactive, and it wouldn't stick around. So that doesn't appear to work. Sometimes people will suggest making it into a ring, 3 as a triangle. Which does allow you to sort the bonding out, but unfortunately, a triangle like that has such distorted bond angles. Those bond angles should be much bigger, and it pulls things in far too close, and so very unstable. So actually, the trick here is a dative bond. So look at O2. Can you see how we could get another oxygen on there with a dative bond? So if we have our oxygen with its double bond and the lone pairs, we can simply have another oxygen plug on, not involving any of its own electrons. So its 6 electrons are 3 lone pairs. And so we have a dative covalent bond. So that's the most straightforward way of thinking about ozone. So you are supposed to be aware of ozone, the formula, and the sort of be able to propose a dot cross diagram. In reality, how the electrons are arranged is often a little bit more complicated than we do in these dot cross diagrams. And in ozone, you might well see that both sides of the middle oxygen behave somewhere between a single and a double bond as electrons kind of flip around the place, but you can't represent that on a dot cross diagram. So we do that. The other thing you should be able to do with structures like this is turn them into a full structural formula. So instead of showing electrons, you show lines for bonds. So do you remember how dative covalent bond work? What would this look like if you drew the molecular structure as a full structural diagram? Just pause the video and draw something. Okay, and you should draw two lines between two of the oxygens as the double bond. And then the dative bond is a single bond, but remember we do it as an arrow, and it goes from the atom that's providing the pair to the atom that's kind of receiving them. So it would be something like that. Right. You then need to be able to discuss reasons for the presence of ozone in the atmosphere. So why is ozone found in the troposphere? Okay, so here's a moment to revise quickly. Turn your mind back to the developing fuels topic. Pause the video. Can you remember at all why we end up with ozone as part of that polluting process? Okay, so you should remember that this is found in photochemical smog, so a component of photochemical smog. So as we've said, it's not a good thing in the troposphere. It's a secondary pollutant formed as a result of primary pollutants made in things like car engines. Do you remember why it's considered bad? Why do we think of it as a pollutant? What's its key problem? The thing to say there is that it's toxic. And the how it actually forms is that it forms when hydrocarbons, e.g. the unburnt hydrocarbons from car engine use, react with nitrogen oxides in the presence of sunlight. Okay, so that's the troposphere. So the key message here is that ozone in the troposphere is bad, as far as we're concerned, because it's toxic. We don't want it there. It has no useful role to play. Ozone does have some uses in the troposphere in a controlled way. For instance, if you ever have a house fire, and apologies if that's a traumatic thought for you, smoke damage is often one of the big parts of it. The smoke that swirls around has a very strong smell, and that smell clings to things. The molecules effectively that are being transported around in smoke soak into books and stuff. They have very strong odor, and ozone can smash those molecules up. So they'll often take smoke damaged things, the things that are smelling unpleasantly of smoke, and put it in a special chamber and put ozone in, and that smashes up those molecules, gets rid of the smell of the smoke. There you go, fascinating fact. But what we actually need to look at is why is ozone found in the stratosphere? Oops. So this will be probably new to most of you. So just put on your best learning hour. And as with everything else, you might need to go over this a little bit, a few times in order to make sense of it. There is a set of reactions that happen. So there's a pair of reactions. The first one is the oxygen reaching the stratosphere, which, if you think about it, why is that oxygen appearing? This is effectively made by plants in photosynthesis. If it wasn't for plants and photosynthesis, oxygen is a reactive gas. We wouldn't really have any oxygen in the Earth's atmosphere. Plants are making that, obviously, down at the Earth's surface, and then that moves up through the atmosphere. If you expose that to high energy UV light or high frequency UV light, then it can smash up into two oxygen atoms, which, if you think about it, do the dot cross diagram, are radicals. In fact, just pause the video, prove that oxygen atoms, individual oxygen atoms, are radicals. And what you should do there is say, okay, oxygen's in group 16, 6 electrons in the outer shell, 1, 2, 3, 4, and not pairing up. Remember, the electrons spread out between orbitals, and in the outer shell, there's effectively 4 orbitals, the s orbital, and then the 3 orbitals that you get in the p subshell. So the electrons spread out. So we have unpaired electrons. And so this is radical. You could call it a biradical because it's got 2 unpaired electrons. What about that high frequency UV light? Where's that coming from then? Talked about this in a previous video. What's our source of the high energy, high frequency UV light passing through the stratosphere? And you should say that's coming from the sun. So think about some vocab we've learnt recently. What type of bond breaking then must be occurring in this process? The type of bond breaking involved. If it produces radicals, there's 2 types of bond breaking that you should know about. Clue, they both have the word lytic in the name, or the part of the name saying lytic. So the type of bond breaking is homolytic bond fission. How do we know that? Because we've produced radicals. Heterolytic bond fission produces ions. What about the type of reaction? What type of reaction is occurring here? If high frequency UV light is smashing up oxygen molecules into oxygen radicals, what type of reaction is it? It's easy to get mixed up between these terms. It's a photodissociation reaction. And there's one more bit of vocab we can practice here. What type of radical reaction step is this? If you look at the reaction, key thing is to look where there are and aren't radicals. So do you remember the 3 types of steps in radical reactions? Something to do with beginning things, something to do with keeping things going, something to do with finishing things. So hopefully you spotted this as an initiation reaction. It's the beginning of a radical reaction. Why? The definition is the reactant side has no radicals and the product side does have radicals. So we've gone from a situation where there wasn't any radicals to a situation where there now is radicals. So we've started a radical process. So it's an initiation step. Okay, step 2 in our why is ozone found in the stratosphere is that those oxygen radicals can then bump into an undissociated oxygen molecule, and those 2 can react together to make O3. So this is simply the 2 things coming together. So this is just about new bond forming reaction. So if you think about it, this step will be exothermic, whereas this one was a bond breaking reaction. Breaking bonds requires energy, so that's endothermic. So as a fascinating little fact, here. In the stratosphere, sunlight, the high energy UV, provides the energy to break bonds, and then as the ozone forms, that's released as heat energy. So strangely, if you were to work your way up through the atmosphere, it gets colder and colder as you go up through the troposphere. But then in the stratosphere, it starts to warm up again because of this way that sunlight, the UV from the sun, is being converted into heat energy. Okay, so that's that process overall. That's how ozone forms. So just quickly recap that. Totally different. So in the troposphere, it's a pollutant. Things from like car exhaust, nitrogen oxides, hydrocarbons reacting in sunlight to make ozone toxic, bad. Up in the stratosphere, they're a natural process. O2, which you're finding up there because we have plants on Earth doing photosynthesis, turning carbon dioxide into oxygen effectively, gets split up by high frequency UV light from the sun to make oxygen radicals, and then those bump into further oxygen molecules to make O3. If you want to write an overall equation for this, rather than looking at the two steps in much detail, you can just be logical. If you are taking O2 molecules, that's the only things being fed in here is O2, and you're making O3, that doesn't balance. So you can just do a bit of simple balancing and say, well, 3 of these will make 2 of these, just on a purely balancing the atoms kind of way. Okay. The other thing you need to know about ozone in the stratosphere is why it's beneficial. So the benefit to humans, or to life, in fact, of stratospheric ozone. I don't know. Do you know anything about this? Scratch around in your head. Have you heard anything at all why it's important to life on Earth that we have ozone in the stratosphere? And so the answer is this, that the ozone absorbs high energy UV radiation from the sun. Do you remember from the previous video what happens when molecules absorb high energy UV radiation from the sun? Well, any high energy UV radiation. We've been talking about it a lot recently. Causing the molecules to photodissociate. So we can write an equation for that very simply. It's the reverse of step 2 in how ozone forms. It splits it to give an oxygen radical and an O2. So this is the reverse of the ozone formation reaction. So what? That's fascinating. That's going on up in the stratosphere. Why do we care? So the point is this prevents most of the high energy UV radiation reaching the Earth's surface. Why don't we want that to happen? Well, it's high energy UV radiation and it smashes bonds up. So you can say, well, okay, so it gives us sunburn. Yes, but it does worse than that. The high energy UV radiation can cause DNA mutations. So bonds that it smashes can be in your cells, in the DNA, leading to skin cancer, etc. So the key idea is a high concentration of ozone in the stratosphere means a lower risk of skin cancer, which is a good thing. A quick fascinating fact for you. If you do evolutionary biology, you will read that the simplest forms of life evolved in the sea. And there's a very good reason for that. High energy UV radiation doesn't penetrate far into water. And so without any plants, there wasn't oxygen in the Earth's atmosphere. All the oxygen reacted and was bound up. It's like carbon dioxide and things. So there wasn't ozone in the stratosphere, which meant that high energy UV radiation, nothing was absorbing it. So it reaches the Earth's surface and smashes everything up. It was only down underwater that complicated molecules could form without getting smashed up. And so as those processes happened, and then simple plants evolved, aquatic plants, so algae and stuff, they then started photosynthesizing and releasing oxygen, which then went up into the atmosphere. And the processes we've mentioned up here happened to form ozone. So then the concentration of ozone in the stratosphere grew, filtering out, well, not filtering out, absorbing that high energy UV radiation, and therefore making the Earth's surface habitable without being bombarded by that high energy UV. So now life could actually progress onto land as well. So nice little tie up between some chemistry and some biology there. Okay, that'll do for this video. Do review it once or twice to make sure it makes sense to you. Write down any questions you have. Obviously, I'll be entirely happy to support problem solving with this. So please just log things that you think, doesn't matter how much I look at this, Marcus, that bit is not making sense to me.